So a couple of things before we get started. One is that I'm going to be recording this on two different computers to see what the audio quality between two is like, to see if there's one that's better than the other. One is my office computer and one is personal computer. So I'll let you know which one gets posted. Because I'm using two different computers, I'm going to be going back and forth between screens to advance the slides, and just to try to keep both of them up to the point in the lecture, on the same even plane. The other thing is that the Radiographic Calculations book has a lot of old terminology in it that you just need to be aware of. There's not another book quite like it, and it just needs to be updated. It's needed to be updated for a very long time. But things like anytime you see F, it's either going to be film or focus. So SID you may see referred to as FFD, which is focal film distance. Source to image distance means the same thing. So don't let that throw you. Just kind of substitute those things. Object image distance may be OFD, which is object film distance, instead of image receptor distance. So don't let those things kind of sideline you. So if I can figure out how to advance this. All right, so I'm not going to spend just a tremendous amount of time working through the things that you should know, things like calculation of mass. One of the things that you see in the book is that this formula is actually upside down. I find it a little bit easier to work this formula and keep things straight if it's set up like this, where mass is on top instead of bottom, with MA and time on bottom instead of top. So that book has it flipped around where MA and time are on top and mass is on bottom. To me, this works out to be a better actual mathematical equation, MA and time over mass, or mass over MA and time, so that you can plug in one of those two, whichever one's missing, and the unknown would be X, and then solve for that. So again, I'm not going to go through each one of these slides individually. I'm going to kind of sum them up, but pretty much what this particular quiz is going to be over is everything that you learned in your first semester imaging class and your first semester intro class and your second semester imaging class. So this is kind of tying all that stuff together, and the big takeaway from this particular PowerPoint and this particular lecture are compound questions that you're going to have on this next quiz, and certainly on the math test week after next. So that's what we're going to spend more time on, and just kind of pointing things out. The idea of this particular PowerPoint is to show you all the different steps and hopefully prevent you from being overwhelmed on that quiz, and certainly on the test too. The test is a 40-question test, and it's going to take you all of 2 hours to work through it. So some compound problems on that. There's some basic problems as well, but there's some compound problems too. So calculation of mass is just MA and time. Just solve for the unknown in order to get your time. Remember that we've got fractional times are usually on single phase equipment. So you just don't work with that all that much anymore unless you're assigned to a clinic, or if you're working in a clinic or a rural location where they utilize single phase equipment. So how you can work that and convert that is to work out your fractions. You remember, a fraction is just a division problem. So you divide the numerator by the denominator and come up with your decimal point, and then you can divide that into the new numerator. So your denominator then becomes 0.2, and divide that into 20. All right, so where we're going with this one then is not just calculation of mass, but what happens as you change your KVP, what happens as you change your mass, what happens as you change your distance, be that OID or SID, what happens whenever you change grid ratio and potentially screen speeds, possibly increase OID as well. So that's kind of where this particular presentation is going. So I'm going to skip through the mass calculations and kind of get to where it is that we're going to spend most of the time today. So this last quiz certainly had changing mass by percentage. Don't make the same mistakes that the first video kind of went through. The difference by changing by percentage and then a percentage of. So if you increase by percentage, then it's always going to be more than the original value. So whenever you're increasing by percentage, then you can just essentially make that 115% in this case, which would increase your percentage by 15%. Remember, the whole is represented by 1. So if you're looking at 100 and you're looking at 100% of 100, then all you've got is 100. So if you increase 100 by 15%, then you're going to have 115%. So don't confuse that by how much is, say, 15% of 100. 15% of 100 would be 15. So if you increase by percentage, you have to add in that original value back, just like what was on the previous quiz. So reduction by percentage, kind of the same thing, but now it becomes a subtraction problem instead of an addition problem. So reduce 100 by 15%. So you can do a couple of things. One is that you can just work it out longhand and say 100 times 0.15 and then subtract that from the 100, and that gives you your 85 mass. Or if you're working with a calculator, then in most cases your calculators, you can type in like 100 minus 15, hit the percentage sign, and it'll give you your overall reduction. Understand, some of your calculators are going to require you to hit the equals sign after you hit the percentage sign, and some of your calculators are not. Some of your calculators, if you hit the equal sign after you hit that percentage sign, it's going to basically give you a double reduction. So pay attention to your calculator and see what's happening. If you type in 100 and you subtract 15, you hit the percentage sign, it gives you 85%, then that's as far as you need to go with it. But if it just leaves you at that 15%, you're probably going to, or 15, you're probably going to need to hit that equal sign. Conversely, if you hit the 15 and then the percent, and it drops you to 85%, then, or 85, then what's going to happen if you hit that equal sign is it's going to drop it by another 15%, which is probably going to put you around 70, 72 or so. That's just a ballpark figure. So anytime that the percentage is over 100%, then again, it's going to be in addition to the original. So certain things are always going to be over 100%, and those things would be like your magnification factor. You're never going to have a magnification factor that's less than 1. And that is because your object size is always going to be smaller than your image size. And that's the actual magnification, not necessarily the display magnification. If you were to take the measuring tools and actually measure the size of the image, then, or the size of the projected image, then it should give you actual magnification. And the reason for that is you can't remove all OID. On hands even, you're going to have a little bit of increase hands and fingers. You're still going to have an increase in OID, that's object image distance, OFD according to your book, but because of the skin, you're going to have an increase. Chest x-ray is going to be pretty dramatic, lateral C-spine is going to be very dramatic, so you're always going to have some magnification present. So your magnification factor is always going to be 1 point something. If you're talking about percentage of magnification, though, then that's not going to be 1 point something. That's going to be just the percentage. So don't confuse those two. A percentage of magnification is just that. It's how much bigger is the image size than the object size, as opposed to the overall magnification. And magnification factor is always going to be 1 point something. So let's get through this and get to kind of the meat of what we're going to talk about in this particular presentation. So contrast. Remember, we've got contrast and density. We have to be able to visualize both of those. Contrast means difference. So if you've got contrast, that means you can see the difference between two different things. You can see bone and you can see soft tissue. You can see bone versus air. You can see air versus soft tissue versus soft tissue. You can see psoas muscles versus kidneys, things like that. The reason that you can see those things is because of differential absorption. Differential absorption, sometimes referred to as K-edge, is really how dense and solid the organ system is and how many X-rays will be absorbed in that tissue type. So bone absorbs more tissue than soft tissue, which absorbs more than air. So that provides us with a change in differential absorption between those different tissue types so that we can see those different things. When we're talking about contrast, we're talking about difference. Density just means how dark it is. Like my shirt is black, it's very dense. The windows behind me aren't so dense, so they're very light. So we can see, let's go this way, we can see the difference in those colors because this is black and that's white. So there's a lot of contrast there. High density, low density, the difference between those is your contrast. So when we're talking about short scale contrast, what we're talking about is very high contrast. So your extremity work should be very high contrast. If you're looking at a chest X-ray through a rib algorithm, it should be very high contrast. The bones should stand out very well. And that is short scale contrast as opposed to long scale contrast. Think of your KUBs on your hypersthenic patients where you've got a lot of scatter creation and it's so gray that you can't make out the kidneys. You barely make out the psoas muscles. So that would be your long scale contrast. High contrast means short scale contrast. It just kind of gets a little bit confusing. High is short, low is long. So low contrast is long scale. It just means essentially that there's not a whole lot of difference between different densities. So they just kind of all run together. It looks gray. It looks kind of milky. Latitude follows low contrast. So where we have high latitude, we have low contrast. So again, it gets very confusing because short means high, long means low, and low means long scale of contrast and low latitude. So what controls contrast then is really your computer algorithm. It used to be KVP. You may see that referenced in your book, but it really doesn't control it in a digital world. Again, that book was written when screens and films were used, and the main controlling factor for contrast was anything that changed differential absorption inside the patient. If we had more absorption, then we had higher contrast. If we had low absorption, that means we had high KVP, and we had low contrast. So you may see that referenced in your book, and that's what it's referring to. But really, the computer algorithm controls it now, and what influences it would be anything that would prevent scatter from being created or clean up scatter after it's already created. What in the world? Okay, so things like grids, things like you may have a marginal influence on contrast with KVP, and I apologize for kind of stuttering through this. I think that one of my recordings shut off, so I apologize for that. So does high contrast carry more or less potential information than low contrast? Well, in a simple, single, concise word, low contrast carries more potential information. Now, the reason for that is the higher the KVP that you have, the more tissue types that you can penetrate, the more likely you are to be able to visualize that contrast. So the higher the KVP, the more, previously, the higher the KVP, the more grayscales that you would have, and the more potential information that you would have. The problem with too high contrast is that if you don't get the penetration, you can't see behind the bones, again, on, let's say, a rib x-ray, then you can't really make a diagnosis of what's going on inside of the lungs behind that tissue, behind the ribs. So with KVP, we can affect differential absorption, and in that affecting of differential absorption, we can affect exposure. So with a 15% increase in KVP, we double the exposure to the image receptor. Now, it's important to note that you don't necessarily double the exposure to the patient with a 15% increase in KVP, but you do change the image receptor exposure. So if you had a question that said that you wanted to change the image receptor exposure using only KVP, what would you do? And that would be to increase KVP. If you wanted to double it, it'd be about 15%. We kind of confuse KVP or make it more complicated than what it necessarily has to be, but a 15% increase in KVP doubles our image receptor exposure. So when we have an increase in mass, we have to use 100% in mass to double the image receptor exposure. And we always tend to lock in on the minimum change to see any kind of significant difference, or any kind of, not a significant difference, but any kind of difference at all, is a 30% change in mass, which is roughly 1/3. Well, 1/3 of 15% in KVP is 5. So a 5% change in KVP shows us a minimal change in exposure. A 15% change in KVP is going to double that exposure. So 15% change in KVP is equivalent to a doubling of the mass. So if we need to change the image receptor exposure, and that's the main thing that we need to change, then we just need to increase our KVP. If we want to change our image receptor exposure and the patient exposure, maybe everything was too low, then what we're going to need to do is increase KVP and maintain the same mass. But if you need to increase the image receptor exposure and reduce the patient exposure, then what you would need to do is increase KVP and reduce mass. So that's your 15% rule. 15%, don't conflate 15% rule with 15% change in KVP. If you increase your KVP by 15%, then you're going to double your image receptor exposure. But if you increase your KVP by 15% and cut your mass in half, then your image receptor remains the same and your patient exposure goes down. So if you need to change, if you need a change in patient exposure with no change in image receptor exposure, then what you use is truly your 15% rule. You increase your KVP by 15% and you reduce your mass by a factor of 2. That's your 15% rule. So using mass, how much of a change for minimum difference? And that is your 30%. Remember, you got 30% as the baseline for the minimum amount that you would change. You're almost never going to use that, because if, it's a testable question, but if it comes down to the point of making a second exposure on a patient, then what you're going to have to change then is your mass by a factor of 2. So it's going to be 100% change. So if you used 5 mass and your your index number indicated that you underexposed the patient to the point that it affected the image and you needed to go back and make a second image, then what you're going to have to do is increase your mass by a factor of 2. So minimum difference on KVP, we just walked through that. With KVP, it's a 5% change is your minimum. Again, you're never going to use that, but if you need to repeat an image because you underexpose the patient, then it's worth changing your KVP by 15%. Remember, 15% equals a 100% change in mass. 5% change in KVP equals a 30% change in mass. So what you're going to look for is primarily your index number, but your index number is dependent on the overall quality of your exposure to your image receptor. So if your index number shows that you made an adequate exposure, but your field size is enormous. Let's say you shot a hand. This is a bit of hyperbole, but if you shot a hand and you used a full-sized image receptor and you didn't collimate, then your index number is going to be based on all that direct exposure plus a little bit of exposure to the hand. So it's going to show probably that you greatly overexposed the patient when you may have used the perfect set of technical factors. So your index number is an indication of what your image receptor exposure is going to be, or is, but it's not the end all for your image receptor exposure. So keep that in mind. If you are using your index number as the be-all for your image receptor exposure, make sure that everything else is right first. So if you're using mass and you want to affect a change in your index number, then you're going to have to increase your exposure by a percentage of your mass. Usually it's going to be, if you're increasing, it's going to be double. If you're decreasing, it's going to be half. With KVP, it's again going to be a 15% increase or a 15% decrease. Now, some of your questions are going to ask you to use both. So let's say you've got a situation where your index number indicated that you overexposed a patient by a factor of 4, and you want to use both your KVP and your mass, and that to correct for it. Then in that case, you would decrease your KVP by 15%, and you would cut your mass in half. So you're not really going to manipulate contrast, but you can manipulate exposure with KVP using just what I've mentioned. So I'm going to go on through this and get to these compound questions that I mentioned before. So what if we want to increase differential absorption? Differential absorption is going to be controlled by your KVP. So again, that's to increase your K-edge absorption. To increase your differential absorption, you would need to decrease your KVP. So what if we wanted to increase differential absorption and increase image receptor exposure by 30%? Okay, so when you get to these complicated questions, what you need to do is just take them one piece at a time. So we're going to add to this question pretty repeatedly through the end of this slideshow presentation, the end of this PowerPoint. So what if we wanted to increase our differential absorption and increase image receptor exposure by 15%? We started off with 100 kVp, 10 mass technique, and it requires more differential absorption. That says contrast, but it's more differential absorption and a 30% increase in exposure. So what you need to do, again, is take this one thing at a time. If we want to increase differential absorption, stop there. So increase differential absorption, we have to decrease our KVP. So don't overcomplicate things. If I didn't give you a percentage of, how much of a change that you need in a certain thing, just assume that you're going to use the standard 15% for KVP, 100% change in mass, or if you're decreasing your mass, then it would be by a factor of 2, just cutting it in half. So 100 kVp, 10 mass, and you need more differential absorption and a 30% increase in exposure. That's image receptor exposure. What would your new technique be? So just take it one thing at a time. So reduce your kVp by 15% and then double the mass. That brings you back to the original technique, and then you've got to add 30% on top of that. So typically whenever you're just increasing your image receptor exposure, that's going to be your mass. So just take it one thing at a time. So reduce your kVp by 15%, and then double your mass, and then add your 30% on top of that. So unless I'm asking you specifically to change your image receptor exposure with kVp, always assume it's going to be mass. So now we've got a new technique that's going to be at 85 kVp because we reduced our kVp, we doubled our mass, and then we added 30% on top of that. That brought us 26 mass. So then you get to this, so you need to increase your differential absorption, increase your exposure, now because you increased your mass, you got a motion problem. So how do you control motion? Well, with careful instructions. And if that doesn't work, then you're going to need to reduce your time. So how do you reduce time while maintaining your same exposure? And that would be by manipulating MA and time. That's your reciprocity. Remember, reciprocity means give and take. So if you cut your mass in half, you're going to have to double your time. If you double your mass, you're going to have to cut your time in half. So that's going to give you the same mass. So now we've got a new set of factors. So our original was 100 kVp, 100 MA in 1 second. The original technique didn't really break it down like that, but now we need less exposure time due to motion. We need that increase in differential absorption, not contrast. I meant to edit all that out. I thought I edited all that out, but I did not. And a 30% increase in exposure. So again, there's an old saying, how do you eat elephant? And that is just like you eat everything else, one bite at a time. So take it one thing at a time. Well, if you need to increase differential absorption, stop. What does that mean? If you need to increase differential absorption, you need to decrease kVp. So walk through that, decrease your kVp by 15%, and then double your mass because you want to bring it back up to the same exposure. Now increase your mass by 30%, and now you're going to need to change your MA station and your time to decrease your exposure time. So we're going to continue to add on to that as we go along. So remember, you've got two different square laws. One is the inverse square law, and one is the direct square law. The inverse square law is what we use to calculate changes in exposure, occupational exposure. Could be patient exposure, but a lot of cases can be occupational exposure as we change distances, right? So image 1 over image 2 is equal to distance 2 over distance 1. Notice that they flipped. Image 1 in the formula will be directly across from D2, and then intensity is really intensity. Intensity 2 is directly across from D1. So the most common mistake that you're going to make in the inverse square law is to not square the second half of this. Or the second most common mistake is going to be that you're going to apply the wrong law. Instead of applying the inverse square law, then you're going to apply the direct square law. So inverse square law always has to do with exposure. So and most of the time you can spot the inverse square law questions by looking at the what the question's asking you. What is the MR? What is the gray? The exposure to the patient or the exposure to the technologist. So remember, anytime, because it's the inverse square law, the inverse square law says the intensity of radiation is inversely proportional to the square of the distance, which means as you increase your distance, the exposure is going to decrease, and it's always going to decrease by the square of the distance. So if you double your distance, then double of 2 means 4. If you double your distance, then your intensity is going to decrease by a factor of 4. So it's pretty dramatic. As one thing goes up, the other thing goes down. Don't forget to square it. Inverse square law, as your distance goes up, your intensity is always going to go down. The direct square law is kind of like your maintenance formula. So it's previous, I guess it really should be changed to exposure maintenance formula. And that is, you can spot these with mass. Okay, so what is your new mass as you change your distance? So that's your density maintenance or your mass maintenance or your exposure maintenance. So because we lose exposure as we increase our distance, we have to add that back in. So notice then that our mass and our D1 are directly across from each other. Mass and D2 are directly across from each other. So it's no longer inverted. You still have to square it, but because we decrease our intensity as we double our distance, what we're going to have to do is increase our mass by the same amount. So if we increase our distance by a factor of 2, then we're going to have to use 4 times the mass. If we decrease the distance or half the distance, then we're going to have to use 1/4 of the mass. So what it works out to be is our most common 2 distances are going to be 40 to 72 inches. We talked about that in physics and imaging 1, but our changes are going to be 3.24. So if we go from 40 to 72 inches, then you're going to need to increase your mass by a factor of 3.24. Whereas if you go from 72 inches to 40 inches, you're going to need to decrease your mass by 3.24. So if you have a radiation dose at 40 inches, your radiation dose at 40 inches is 20 MR, what will the dose be at 36 inches? Okay, so the first thing that you need to focus on is the MR. Okay, so it's not asking you about mass. This is asking you about milliroentgens, which is exposure. So, and it could be milligray, but it's not asking for mass. So you've got to assume that this is going to be your inverse square law. So as we decrease our distance from 40 to 36 inches, then what's going to happen, since we've decreased our distance, what's going to happen to our dose? And that's going to be that it's going to increase. And it's more dramatic than you might think. You know, at just that small amount from 40 to 36 inches, your dose goes up by 5, which would really be about 25%. And that's pretty significant for that little bit of a change right there. So if you remember back to the second semester, first semester even, when we were talking about radiation dose and fluoroscopy, and that's really where most of your radiation dose should be coming from. There's not a whole lot of reason for you to be in the x-ray room while the x-ray beam's energized unless you're doing fluoroscopy. Then a single step back means a lot of dose reduction. So anytime you don't need to be right up on the patient whenever fluoro is being used, step back and get away from the x-ray table because your dose is coming off of the patient in the form of scatter radiation. So just a single step back, I mean, this is 4 inches, right? So this is 4 inches, and the exposure difference in that 4 inches is 25%. So, you know, if you take a 2-foot step backwards, it's going to decrease pretty significantly. Get away from the patient whenever fluoro is being activated. Just no reason for you to be right up against the patient. So there's some problems in your textbook that I kind of directed you towards. Rounding mass, really on the quizzes, if you get close, if I can tell what you've done, then chances are I'm going to give you credit for it. So I'm not going to be a real stickler on rounding. So again, how much of a change does it take to see a visible difference with mass? That's going to be your 30%. Is it critical to get exact mass, or is it okay to round it? Well, no, it's not real critical. If you notice, most of your machines won't get to the exact mass that you would want in a lot of cases. So, like some of your machines may give you 2.6 mass. Well, what if you needed to double 2.6 mass? You'd have to get to 5 mass. But a lot of your machines won't get to 5 even. It may go to 6. So is that really going to be a problem? And the answer is no, because it's going to require 30% change just to see the minimal amount of change on the image receptor. So that change from 5 to 6 is only going to be 20% of change. You don't really want that 20% change, but you can't get around it. So you're just going to have to deal with it. So when you need to decrease your decrease in contrast, previously that would be a decrease in differential absorption and decrease your image receptor exposure. Things are going to get pretty dicey. Okay, so just make a mental note. Decreasing contrast means to make a longer grayscale. Previously, that was with KVP, with a higher KVP. So now what they're looking at here on these problems is decrease in differential absorption, or a decrease in differential absorption, which would be an increase in KVP, and a decrease in your image receptor exposure. So if you increase your KVP, your image receptor exposure goes up. So let's say you increase your KVP to accomplish this, the decrease in differential absorption. You increase your KVP, you're going to increase your image receptor exposure. So then what you're going to have to do is decrease your mass by really a factor of 4. So you cut it in half and then cut it in half again. So if you had 100 kVp at 100 mass, let's say, it'd be a pretty high exposure. And you needed to decrease contrast, decrease your differential absorption, then you would increase your kVp to 115. And then you would take your mass and you would decrease it by 50%. So it would decrease, instead of being 100 mass, it'd be 50 mass. And that would bring you back to the original exposure, but you would need to decrease it again to bring it down to a decrease in your image receptor exposure. So we're back to this thing. So what if you needed an increase in differential absorption, an increase in image receptor exposure, decrease in motion, and you changed from 40 to 72 inches? Well, I'm going to run through all this stuff, and we're just going to focus on this. Again, just go through it one step at a time. If you read the entire question and it's something that looks like this, it's going to scare you half to death. So just take it one step at a time. So you do all the stuff that you did before, and then you change from 40 to 72 inches. So what do you need to do if you go from 40 to 72 inches? And that would be that you would need to increase your mass by a factor of 3.24. So you do all the stuff you did before, and then you would multiply your final mass by 3.24. And you can do that, before you change your MA and your time, if you like. So one other thing, there's a couple other things, but one other thing that you're probably not going to run into is image receptor speeds. So where you see image receptor speeds are really in the unlikely event that you work with both a CR system and a DR system. What image receptor speed means is the relative speed or sensitivity of the image receptor. So if you're looking at a CR system, CR systems require, if you happen to still work with one, I think we have one clinical site that still has a CR system. The CR systems require naturally about double the mass that a DR system would. So CR systems are slower than what a DR system is. So if you were to use all of that technique in a CR room and then you were to move to a CR system, then essentially what you would do is cut your mass in half. All right, so and that's pretty much what all that runs through there is that you would again need to cut your mass in half. So it's just one more step. Just take it one step at a time. One thing that you may run into actually is grid ratio though. So grid ratio or changing grid ratio or addition of a grid. So the purpose for a grid is to absorb X-rays before they make it to the image receptor. So your index number is going to be formulated based on every photon that strikes the image receptor. So it may be scatter radiation, it may be direct exposure, and it may be penetrated unscattered X-ray photons. It doesn't really matter. Whatever strikes the image receptor is going to go into the formulation of your index number. So those X-ray photons that strike that are scattered are going to be a part of that formula that gives you your index number. So the purpose for the grid is to absorb some of those scattered photons. The scattered photons are going to affect your image. So if we absorb those scattered photons, we got to deal with that. So the things that affect scatter radiation, really, your KVP is going to affect the ratio of your scattered versus your penetrated versus your absorbed photons. So as KVP increases, just in a word, we're going to get deeper into this as the semester progresses, but in a word, as KVP goes up, scatter radiation goes up relative to the other things. Again, it gets deeper than that. So if you're watching this and you say, well, we're going to get into that later on. But just for now, we're going to say as KVP increases, scatter is going to increase. Also, tissue type affects your scatter radiation. As we get a tissue type that's more akin to soft tissue, we're going to increase our ratio of scatter. So we're going to get more scatter radiation with tissues that are more water filled as opposed to air bone. And then we've got a couple of different rules of thumb for grid use, and that would be if your tissue is 5 centimeters or above, so essentially knee size or shoulder size, or if we're using 70 kVp or above, then we probably should be using a grid because we create enough scatter radiation that we should. Now, I'm going to go ahead and, this usually comes later in the semester, but I'm going to go ahead and say a couple of things about both grid use and the industry standard in using mass for technique adjustments. Number one, since KVP and even grids aren't your primary controls of contrast, it's really the computer algorithm, there might be some adjustments eventually to those rules of thumb. And you may see those in your career. That 5 centimeters and that 70 kVp may be adjusted. And number two is that since KVP doesn't control contrast anymore, then you might see in your career a change in which technical factor you may use to adjust exposure. So let's say right now, you have a hypersthenic patient, you tend to increase your mass to compensate for that hypersthenic patient. And I believe in your career, you're probably going to see more of a dependence on KVP, especially as they dial in things like virtual grid and things like that and make them more effective. So what does a grid do for image quality? Well, if it increases your contrast, it improves image quality. So the elements of your image quality are basically sharpness of recorded detail, visibility of recorded detail, density, contrast, those things. So what does it do to image receptor exposure, which equates to density, is that as we increase our grid ratio or we add a grid, then our exposure decreases very dramatically. And that's because it absorbs that scatter radiation. So the scatter radiation, even though it's bad, it does go into formulation of that index number. So it might change your contrast as we add a grid, because it absorbs that scatter radiation, it might change your contrast just a little bit. Visibility of your contrast may change a little bit. Again, your algorithm is going to be your main control of that contrast, but it may increase your contrast a little bit. As you change grid ratio and go from a low ratio grid to a high ratio grid, it potentially could affect both of those things as well. And so as you change from a low ratio grid to a high ratio grid, then you're going to absorb more of that scatter radiation, and that's going to give you a lower index number, or index number that indicates that you underexpose the patient, and possibly improve contrast a little bit better. So the technical factor that we use right now to compensate for grid use is always going to be mass at this point. Again, that might be KVP at some point, but at this point it's still going to be mass. So how that's going to affect patient dose is going to be a very dramatic increase in patient dose. So as we add a grid, let's say an 8-to-1 grid, if the Bucky factor for that grid is 3, then what that means is that we're going to use 3 times the mass to get the same image receptor exposure with the addition of a grid. So again, I think that as virtual grids become more effective, and as the computer algorithms become even more effective, then we're going to see maybe a lower dependence on physical grids and more of a dependence on virtual grids. We'll talk about how virtual grids, how they work later in the semester. So grid ratio is one thing that you're going to have a tendency to trip up on grid ratio is the height of the grid divided by the distance in between the grid strips, so the width of the interspace material. So those are the two things that we're comparing, is the height of the grid strip divided by the distance in between. Sometimes you have a tendency to go with the height of the grid strip divided by the thickness of the grid strip, and you're always going to get it wrong. And most of the time, your multiple choice questions are going to come with that as a potential answer. So make sure that you're comparing the right things, the height of the grid strips divided by the distance in between them. So the higher the grid ratio, the higher the number. So a 16-to-1 grid ratio means that we've got more lead in our grid than what we have with say a 5-to-1. With that higher grid ratio, we're going to have more scatter cleanup, which is going to improve our image, potentially, give us a higher contrast. But that also comes with the understanding that our patient dose is going to go really pretty much through the roof. So that's all of that stuff there, and that's a very busy slide, and I apologize for that. Changing grid ratios, you can use the formula new mass equals old mass times 2 over from if you want to. I'm a little OCD, and I always like to take grid ratios out of the equation. So what I would tend to do is, if I had a grid ratio problem, let's say a set of technical factors with an 8-to-1 grid, I would take the grid out of the equation, find my new mass without the grid, and then go back in with the new grid ratio to get my new potential mass. You work it however you want to. So we're back to this thing, and again, the only thing that we need to do here is to now figure out what our grid ratio is, or our Bucky factor is. On the quiz and on the test, I'm going to give you the Bucky factor, so you're not going to have to memorize these. But if you remember back in your Bouchon book, our grid ratio changed with our KVP, and that is because with the KVP, the percentage of scatter was going to increase. So as our KVP went up, our scatter went up, and our grids became more effective. So I'm going to give you the grid ratios so that you don't have to memorize grid ratios at specific KVPs. So all the stuff that we looked at before, you're going to do again, and this time you're just going to add your grid ratio again. And so that's really the last and final step. So where we have geometric unsharpness, our geometric unsharpness is penumbra. Remember, umbra means sharpness, penumbra means unsharpness. So that's your image blur, and the things that are going to control that are your OID, your SID, your SOD, your focal spot size. So your geometric unsharpness is going to be focal spot blur times OID over SOD. Remember, your SOD is going to be your source to object distance. So you have to calculate that. So you're going to have a tendency to go OID over SID, and that's not going to be the case. It's going to be SOD. So you can also calculate it as SID over OID over plus SOD. So there's some problems that you can look at in the textbook again. So magnification unsharpness controlled by the same factors as before. Focal spot size does nothing for magnification, but it does have to do with sharpness of recorded detail. So anytime we have a ratio problem, like this should be somewhat familiar to you. So anytime we have a ratio type problem, so we've got magnification unsharpness. So what we have here is source to object distance. We've got source to image receptor distance. So with magnification and sharpness, what we've got is a ratio type problem. Object size is to image size as SOD is to SID. So that is your formula for it. But let's back it up one and talk about these distances. So we've got source to object distance, source to image receptor distance, and then we've got your image size and your image size and your object size. So where you've got ratio type problems, and that's what this is, it doesn't really matter how you set it up as long as you put the right things across from each other. If you remember back to the first semester imaging, the big is to big, as little is to little, that's where this comes back in. So you can flip this whole thing over, remembering that to solve for a ratio type problem, all you have to do is cross multiply and then divide out and isolate the unknown. So your object size times your SID is one of the things that you're going to be multiplying, and your image size times your SOD. So if you flip that entire thing over, not just one side of it, but if you flip the entire thing over, then what you're going to have is multiplication of the exact same factors. So don't get hung up on exactly which thing necessarily needs to be on top. Object size and SOD can be on bottom, and image size and SID can be on top, and you're still multiplying the exact same things, and so it's going to give you the same magnification unsharpness. So that concludes this. There's spring conversions and things that are irrelevant anymore that I just left in the PowerPoint. So that's what you need to know for next week's quiz, your math quiz, your second math quiz. If I am back next week, then we'll have a quiz in class. If not, I'll probably send it out to you on email the same way I did with math quiz 1.